Hi, yeah, my name is Amy. Today I'm going to show you how to avoid repeatedly writing some recursive code by using the recursion schemes. Yeah, here is the agenda. Some problem. I will point out some problem in some sample recursion example, and then I'll introduce a concept of fixed point, which comes out some fundamental recursion patterns, also known as morphism. And then later on, I will illustrate how to use this morphism by using some recursion example, and then I will introduce some references for further reading. And finally, I will come to a Q&A section. Yeah, just a bit background. Yeah, I'm a Scala developer, some basic knowledge in Haskell syntax. Not familiar with category theory, but very interested in functional programming. In functional programming, recursion is used extensively. However, there is always a lot of boilerplate of making recursive calls. Here is one example. This typical expression example, the highlighted part, they are recursion call, and there is interleaving of recursion call and application-specific logic, and just how to evaluate. And second example is building a factorial number. And again, there is a mix of recursive call and some application logic. Similar situation in the merge sort. And now the problem is, okay, this recursive call repeatedly made and mixed with the application-specific logic. And it would be great if we can filter out this recursive call to make the solution simpler. And if we have another look on this recursion, we can find out that recursion is indeed iteration of nested structure. Therefore, if we are able to identify the abstraction of this nested structure, then the iteration on this abstraction can be filtered out as pattern. And under this condition, we only need to define non-recursive function for our application specific requirement. And then the problem can be solved in a simple way. Yeah. But how? Yeah. And how to identify the abstraction of this nested structure? And the idea is surprisingly simple. It uses a higher kind of type called fix. Here it is fix because it is a higher kind of type. That means the F is the type constructor. What does it mean? It means that I can apply the type fix of F to this type constructor F, such that it turns out I can make this fix of F a nested data structure. And to iterate this nested structure, fix of F, okay, we will expect that F is not just a type constructor, it's a functor. And how F being a functor can make the iteration work. Here it is. Yeah. Okay. In this diagram, the bottom part is our purpose. We want to iterate this nested structure to build up the value. And what happens underlying is we call the unfix of this fix of F according to the type design. And then unfix it, it returned fix of F. Because F is a functor, therefore I can apply fmap with the same, oops. Okay, and I can apply iterate, and then which return F of A. And then the only thing remains is I need to define the function map from FA to A called ALG. And this is not finished yet because our purpose is want to make the function fa to a, which represents this application-specific logic to be decoupled from this recursion pattern. However, there is still something blocking us, is this iterate. Yeah. Therefore, what we can do is just simply replace this iterate by kata ALG. Then now it turns into this way, and this ALG is completely decoupled from the recursion pattern. And what is this kata function? This kata function, here is the signature. Yeah. Yeah, don't worry about the logic. We in functional programming, we only care is the type, and the type, yeah, programming by type. And here it is, that's the type required for this kata function. And this kata function has formal name, it's called katamorphism. Yeah, yeah. This one of the scary thing is in functional programming, there are lots of unfamiliar terms, but they are just a name. Yeah, don't be scared. And this is the first fundamental recursion pattern. And yeah, some highlights on the katamorphism is yeah, the function fa to a is called algebra. It's the long recursive function for application-specific logic. And a is called the carrier of the algebra. Therefore, if we solve a recursion problem by using this kata function, we only need to do two things. First is define the functor f. Second one is to define the long recursive function fa to a according to the application requirement. And how to use it? Here is the example, the expression problem I showed before. Okay, as mentioned before, first we need to define the functor. In this case, luckily, this example is simpler because in the original design there is already an algebraic data type, and therefore it already done most of the things we need to do. And in our case, we only need to redesign this algebraic data type as functor. Therefore, I insert a, yeah, to make it as a functor. And yeah, I just use this language extension because to make it as a functor, that's it. And now, next step, we need to define the algebra for this application. Okay, then what is the requirement? For example, in our requirement, we want to evaluate the expression. That means that we need to we build up an integer value for this evaluation. Therefore, the carrier type is int. Therefore, in defining this algebra, fa to a, the a will be int. We already defined the functor before. Therefore, the functor will be expression f. And now just do the implementation, and yeah, pretty straightforward. Just C and plus and multiplication. And now is how to use it. First is I need to prepare the expression, which is in the fix of f, the last data structure. And then we call the kata, and then passing in the algebra, which is the evaluate function I defined before, and then return same thing. And there is another requirement. What if we want to format the expression? And in to format expression, that means we want to return the string format of this expression. Therefore, in this case, the carrier type is string. And therefore, the algebra will be, again, functor, but this time it's functor string to a string. And then do the same pattern match, and then return the corresponding value. And to format this expression, yeah, it's almost the same as before. We use the kata function expression, but now I change the algebra to format. Then it returned this thing, and looks quite really useful. Yeah. However, it's not done yet because katamorphism sounds too simple. there are still more morphisms is required to solve other kinds of problems. Therefore, now I'll go to the second one, second morphism. Yeah, it's called anamorphism. Yeah. It's opposite of catamorphism. If you think about catamorphism, it's like building up a value from a less structure. Therefore, you can imagine it's like a piece of paper folded up to an object. And anamorphism is just the opposite. It's just an object unfolded into a piece of paper. And here is the structure. And yeah, you can see almost the same as kata, but now is you unfold it to a paper. That means A to fix of F. And also the long recursive function now is A to FA. It's just reverse order as the kata function. And there's a name for this long recursive function A to FA. It's called coalgebra. Yeah. And one of the purposes of anamorphism is for another thing called hylomorphism. Yeah, again, it's just lame. Okay, the idea is very straightforward. It's just the composition of anamorphism followed by catamorphism. What does it mean? For analogy, you can imagine that, okay, I have a robot, let's say a transformer. I want to unfold it to a piece of paper and then fold it to another robot, let's say a Gundam. Okay, then, yeah, that's the hylomorphism is more about. And what is some example can be solved by hylomorphism? Is the sorting, merge sorts. In this case, that's the original code. But in this case, the type is from list to list. Therefore, if we think in terms of hylomorphism, that means that there is this object is a list, is unfolded into a nested data structure by anamorphism. And then this nested structure is folded to another object. Just happen in this case is a list again. And in the second step is using catamorphism. And now we have to think about what is the functor. In this case, there's no functor. It's not trivial, but we can get some hint to think about what the condition we have to cater with in designing this functor. And in this case, the original code, there's only two conditions. Yeah, it's the length, depends on the length of the list. Therefore, what we can do is, okay, in designing our algebraic data type for the functor, actually, to make it easier to do it, there are three conditions. The first condition is the list is empty. Second condition, the list has only one item. Third has more than one item. Then, here it is. There is the functor. That means empty, one item, and then more than one item. And R, in this case, is the carrier type for this functor. And the functor is the 3FA. And now we move on to define what is the coalgebra for this anamorphism. Now we need to define A to FA. And A, because in this example, we need to unfold the object, which is a list, to a nested structure. Therefore, this object is a list. Therefore, the carrier type is a list here. And the functor, which I defined already, is 3f of A. And therefore, here it's just pretty straightforward. You just empty, return empty, and then item 1, use a leaf to hold it. And it is a list. It's almost like what we did in the merge sorting before. It's just break the list into roughly 2 similar length of list, and then to construct the branch. And now, then we need to also consider the catamorphism. Catamorphism, we need to think the algebra. Therefore, is FA to A. And yeah, and again, because in this case is the nested structure, I need to fold up to the object, which is just happened is also a list again. Therefore, the carrier type is the list. And we use the same functor, G of FA, and just do the reverse thing. Is if it's empty list, it's a list of one item, therefore just a list of one item. And then if branch, I use Haskell function merge. That means for the two lists, they can be merged in ascending order. Yeah. And how to use hylomorphism to do the sorting. And here it is. Your hylo, and then the merge is, okay, the type is FB to B. That means the merge is algebra for catamorphism. And the second one is A to FA, which is called split, is the coalgebra for the anamorphism. And then here is the list. Then it do the sorting and return in this way. And last one, yeah, paramorphism. Actually, there are heaps of morphism, but I can only talk a few of them only. Yeah, and the catamorphism, paramorphism. Why we required it is in catamorphism, FA to A, because in this function, we can only access the value A to do transformation or other processing. It doesn't provide the original last structure, which is fix of F, from which the value A is built. And therefore, here is something called paramorphism. It's really similar to catamorphism. You just have additional fix of F here, and that's it. And which we can use this last structure. Okay. Which problem we need to use this paramorphism? Okay, is the factorial. Yeah. In this solving this factorial problem using paramorphism, again we need to define the algebraic data type for the natural number. And what are the conditions required? It is stated here already is n less than 1 or n bigger than 0. Therefore, I defined the algebraic data type, which is the functor is called, I just call it let f, and then pass in the carrier type A. And therefore, there are two conditions, either 0 or succeed A. And to solve this problem, this is a bit, sorry, it's a bit messy, but yeah, just to illustrate how to use the paramorphism. First, we need to think about how to find the natural number value of this let of F first. First, we use catamorphism. If the functor is called 0, then I return 0 value. Otherwise, we just if this succeed n, therefore we simply n plus 1. Second step, this is a handy function because later on it is required in dealing with to calculate the factorial number. Now here it is, the key thing is use paramorphism for the factorial number. And okay, we need to define this function fa fix f to a. And therefore here it is, okay, in factorial number, you know that when it is 0, it will be 1. And then here, if this is succeed of n of x, okay, n is the, what does it mean? It means that n is the factorial value built from the last data structure x. Therefore, now is with init or move on to the next step. Okay, what is the next factorial number will be? Therefore, what it does is I use n times catanet ALG. ALG is what is this function. Yeah, and then call succeed of the x, and then call, because I need to enclose with fix to make it compile, therefore. Yeah, it's a bit, but I want to illustrate how to use the, why paramorphism is useful in some cases. And therefore, now in this case, I prepare the natural number in the last data structure format Therefore, it started 0, and then just that means actually it's find the factorial number of 3. Therefore, now it's called per, and then so on, and return 6. And yeah, and therefore that's the recap of the paramorphism we just discussed. The first is catamorphism, the most basic one. And then endomorphism, yeah, is reverse of catamorphism. Yeah, hieromorphism is just like is the combination of endomorphism followed by catamorphism. And finally, the paramorphism is almost the same as catamorphism, except it includes that additional fix of f here. And all these morphism, they are fundamental, and actually they are already available from the Haskell recursion schemes library. Therefore, if we use this morphism to solve some recursion problem, what we only need to do is to consider the application-specific requirement by designing the functor only and also the long recursive function, and that's it. And of course, in the real world, there are much more morphisms available from the recursion schemes library. And maybe sometimes we find that it's still not sufficient. We may need to consider inventing some ourselves to solve our own problem. Therefore, yeah, try to use morphism to solve the recursion problem to make it simpler. And here it is. Some references I come across. The first few of them, personally, I think is pretty useful for help me to understand especially about why the fixed concept work and so on. The first link is very useful. And the second one is also more practical. It's about how the recursion scheme library are designed. And the third one, I find that it's very interesting because it covers a lot more morphisms. And I forgot maybe over 10 morphisms and so on. And yeah, just the first one is the recursion scheme library from Haskell. Yeah, I would like to mention the second last one. It's a paper. I believe it inspired many of the recursion patterns in recursion scheme written by Eric Meyer and 2 other persons. However, I don't understand it because it's really academic and I don't understand the math symbol. But I think it's, if you are interested to see how people think or comes out this recursion pattern, yeah, it's still good to know. And if you are looking for a challenge and you want to do functional programming in Scala, okay, here it is. It's a recursion scheme in Scala called Matryoshka. I think it's the Russian term is recursion. And yeah, but I haven't saw it yet. Yeah. Therefore, yeah, that's it. It's a bit rushed, and that's all for my talk. And yeah.